Alright, this video is part 3 of Thermodynamics, chapter 5 in the Burdge book. Today we're going to focus on calorimetry, both constant pressure and constant volume calorimetry, how we do the calculations, and the heat equation, and then we'll talk about some of the applications of both. So before we can talk about the process of calorimetry, we have to define some terms, and you need to know these terms and understand the units of these terms. So the first one, specific heat. So all substances have a specific heat, and there is the amount of heat required to raise 1 gram of the substance 1 degree Celsius. So how much heat, how much thermal energy do you have to apply to something for it to get for 1 gram of that substance to raise 1 degree Celsius? And you may be thinking, well, when would I ever use this? Well, a common one is, this is why you do not cook with a metal spoon in a pot of boiling water, because you know if you have a pot of boiling water on the stove and you put a metal spoon in there, you come back 5 or 10 minutes later, that spoon is as hot as the water. So metals tend to have low specific heats because they're good conductors of heat and electricity, and we've talked about why that's the case for metals in previous chapters. So you cook with a wooden spoon. So a wood spoon, wood is made up of mostly nonmetals, and nonmetals are poor conductors of heat and electricity. So if you leave the wooden spoon in the pot for 5 or 10 minutes, you come back, the handle of the wood spoon is still cool compared to the boiling water. So heat capacity is the amount of heat required to raise the temperature of the object by 1 degree Celsius. It doesn't have that mass associated with it. And heat capacity is used a lot in engineering because we want to know not just per gram, we want to know the entire object, how much heat's required to raise that entire object 1 degree Celsius. So the specific heat for water, I would memorize this because notice it's the 4.184 joules, and so hopefully you've thought about this and you go, oh yeah, we defined 1 calorie as 4.184 joules. In fact, that's what the definition of a calorie is. A calorie is the amount of heat required to raise 1 gram of water 1 degree Celsius. And so the specific heat of water is 4.184 joules per gram degree Celsius, or if you wanted it in the British units, it would be 1 calorie per gram degree Celsius. So how much heat is required, or what is the heat capacity of 1 kilogram of water? So if I have a kilogram of water, how much energy do I have to apply to the water to get it to rise 1 degree? So we take the kilograms, we convert that to grams, and we have to do that because the units for specific heat there are joules per gram degree Celsius. So again, this is another important chapter where you're going to have to really watch your units here. And so let me I'm having a little bit of a problem here with the pen. Let me go back. So you can see this is in grams. This has to be in grams, so you convert the kilojoules to grams, so those will cancel out, and you'll get 4,184 joules per degree Celsius. And again, for a number that large, we put that in scientific notation and make it 4.184 times 10 to the third joules per degree Celsius. So that's how much energy has to be applied to this mass of water to raise 1 degree Celsius. So this is an important note right here, is to see that specific heat, again, the mass, heat capacity, the mass is not there because we're assuming how much heat required for the object. All right, you need to memorize these equations here. It's SMAT or CAT, all right? So Q is heat. We already know that. S stands for specific heat. M stands for mass. And again, the mass is going to generally be in grams because the specific heat is in joules per gram degree Celsius. And then this temperature is in degrees Celsius, not Kelvin. Keep it in Celsius. So that Celsius and that Celsius would cancel out. That gram and that gram would cancel out. You're left with joules, which is the unit for heat. So remember, heat comes in 2 units usually. Joules and calories. Joules, the metric unit, calories, the British unit. So for heat capacity, we could also say heat is equal to the heat capacity times the temperature change in the water, or whatever the substance is. And usually we're dealing with water, that's why I said water, but it's whatever the temperature change of that substance is. All right. So memorize these 2 equations. They're not hard. Q equals SMAT, Q equals CAT, easy to remember. So the next slide shows different heat capacities or specific heats. And so notice again, the metals. Look at the specific heats of metals. Very low. Look at gold, 0.129 joules of energy required to raise 1 gram of water 1 degree Celsius. So here's the kind of thing you get into if you're like let's say you're running a restaurant. Notice that copper has such a low specific heat compared to aluminum. So that's why people cook with copper. Copper has such a low specific heat, it doesn't require as many joules of input to raise the temperature of the copper 1 degree Celsius. So over time, this should save you some money if you cook with copper versus aluminum. Now, copper is very expensive compared to aluminum, and maybe you burn your pans or something, or they get so out of whack by the time the copper, let's say you ruin a pan of copper, it's a very expensive loss, whereas an aluminum pan you could easily replace due to the cost differential. Gold would be better, but we don't see people cooking out of gold pots and pans. But look at that. If you could cook out of gold, doesn't take much energy to raise 1 gram of gold 1 degree Celsius. Iron, like a cast iron skillet, well, it's better than aluminum. So here's iron. Not quite as good as copper, so iron is a good alternative to copper pans. And then we have mercury. Well, it's too toxic. Water, look at water. I mean, look at it. It's so large compared to those metals. So once you heat the metal up, if you've got something, if you're boiling water, it's going to take this much energy input just to raise 1 gram of water 1 degree Celsius. And then we have ethanol. And again, we're talking about intermolecular forces and the way that electrons are distributed throughout the systems of water and ethanol. And yes, water has a much higher specific heat than ethanol. So this is the type of question you could be asked to solve. So it says the amount of heat in kilojoules required to heat 255 grams of water from 25.2 degrees Celsius, about room temperature, to 90.5 degrees, just below boiling. So here's what I find students do right off the bat is make sure your answer's in kilojoules. You've got to watch your answers here, all right? You've got to watch your units. So Q equals SMAT. Q is the heat. That's what they're asking for us to calculate, the amount of heat. So we know that we're solving this equation straightforward. So notice they don't give us the specific heat of water. They assume that you have that memorized. So make sure you memorize the specific heat of water. You have 255 grams. The temperature change is always the final minus the initial. And so that's what we have here. And the temperature change is a positive value. So keep that in mind, it's a positive value. You go, why do I need to know that it's a positive value? Because you're going to get for an answer a positive amount, because in order for the water to go up in temperature from 25.2 to 90.5, energy has to be input into the water. And so that is an endothermic process. So we would expect that when we calculate this out, the specific heat times the mass times the temperature change, and again, watch your units. It's really important that you watch your units. You would get this as your answer. It is a positive value, which says that's how much energy has to be inputted into the water for it to boil, or not boil, but to get to 90.5. But they asked for the answer in kilojoules, so this is what they're looking for, a final answer. Or you could write 6.97 times 10 to the 1. Although less than 100, I would just leave it like so, and there's no ambiguity about how many significant figures you have. So this is called a heat equation problem. You're definitely going to have problems like this on the quiz, the exam. The only way these get complicated is sometimes they don't give you this and you have to figure out what this is, or you start combining two heat equations together, which we may see an example of that. Like if I throw a metal slug in of a certain temperature, certain mass, into a cup of water at a certain temperature, certain mass, then we'll have to combine those to figure out maybe the heat exchange or what the temperature change of the water will be, and so forth. So they do get a little more complicated, but it really does come down to this equation, and I think you can do it at this point. It's not the most difficult problems. All right, so let's talk about constant pressure calorimetry. This is what we do in the lab most of the time, because look how simple the apparatus is. It's a couple of styrofoam coffee cups. You have your solution here. You have a stirrer. You can barely see it there, but there's a stirrer there. And then you have a thermometer. And then you have, most of the time, we don't even have the insulator on top. You do lose some heat through the top, but it works pretty well. I mean, maybe get about a 20% loss, but according to the way those experiments work, it's not that major of a loss for the calculation. So, cue the system. What is my system? You have to define it. The system is the water here, all right, or the solution. And whatever, so if the solution, if the heat leaves the water and it causes the thermometer to go up, then that would be an exothermic process, and we would get a negative value here. So the temperature of the water would go from, let's say it goes from 75, well, let's say, yeah, it goes from 25 degrees Celsius to 75 degrees Celsius. Well, 75 minus 25 gives me a positive value here. That's a positive value, and that's a positive value, and overall it's a negative value because, yes, the heat is leaving the water as we go, or the heat. Let's say the system is actually the water is gaining temperature due to the reaction, and it would be exothermic. It'd be giving off heat. So whatever is lost by the system is gained by the surroundings. So if this was a negative 300 kilojoule or joules of heat given off, then the surrounding must absorb 300 joules of heat, again due to the conservation of energy. So if I put negative 300 in here, negative times a negative gives me a positive 300 here. So Q of the system is negative, the specific heat times the mass times the change in temperature. Then the Q of the surroundings would be the positive value of that. All right, so that's what they're trying to tie together here. So I know that may not make a lot of sense. Just keep in mind that, again, you've got the system, what you're interested in studying, and then everything, and then out here is the surroundings. So if the system gives off heat, where does that heat go? Well, the surroundings has to absorb it. So if the system gives off negative 300 joules, the surroundings have to absorb the 300 joules. So let's look at a problem. Again, coffee cup calorimetry. Before we go to that, yeah, let's stress this one more time. Coffee cup calorimetry, called constant pressure calorimetry. And it's not sealed off from the environment. I mean, so the atmospheric pressure is pushing down on the surface of this liquid. We assume that pressure is not changing through the course of the reaction. So that's why we call it constant pressure calorimetry. And it's a very simple apparatus. You can make this at home. All right, so let's look at a problem. This is your classic constant pressure calorimetry problem. So you have a metal pellet with a mass of 100 grams, originally at 88.4 degrees Celsius, so it's warm. is dropped into 125 grams of water that's originally at 25.1 degrees Celsius. So you know by experience that if you put a hot metal object into a room temperature water, the temperature of the water is going to rise, all right? And it's going to rise, it's going to equilibrate. That's what we say, that the metal slug and the water will eventually settle at some temperature. So that temperature says the final temperature of the slug or the pellet and water is 31.3 degrees Celsius. So notice, yes, we lost heat from the pellet, and we've gained heat by the water. And the overall equilibrium temperature is 31.3. It says calculate the heat capacity of the pellet. All right. So heat capacity is the capital C. We're going to use Q equals SMAT, the heat equation, to determine the heat absorbed by the water. Then we're going to use Q equals CAD to determine the heat capacity of the metal pellet. So that's what I'm saying is you're going to see a lot of problems where you have to do like solve two equations and for one unknown. And you go, well, how am I supposed to know this? Well, this is what you're going to do. So I was just start labeling stuff. Q of the water. All right. I don't know what that is, but I do know the specific heat of water. It's 4.184 joules per gram degree Celsius. You're going to have that memorized easy. You know what the mass of the water is, 125 grams of water. And you can calculate the temperature change. Initially, it was 25.1 and it settled at 31.3. So 31.3 degrees Celsius minus 25.1 degrees Celsius, because that's the final minus the initial. Make sure you know that. And you notice that this is going to be a positive value. So Q is going to be positive here. Well, that makes sense because the metal slug transferred the heat to the water, which caused the water temperature to go up. So we would expect that to be an endothermic process for the water. Now, the metal slug is releasing heat, so we would expect if I calculated Q for the metal slug, Q for the metal slug ought to be negative Q of the water, right? Because whatever heat was gained by the water was lost by the metal slug. So think about it like that, and then let's look at the problem. So you may want to stop here, write down all the information from the equation, organize it, make sure you have your units, and then start trying to solve it before you go to the next slide. So that's what they do. This is what I would expect too. You write down all the information about the water, all right, and then you're going to calculate the Q of the water is negative Q of the pellet times the mass of the pellet, and the pellet's 100 grams, and the temperature change of the pellet is, it went from a initial temperature of 88.4 to 31.3, so it's 257.1. And that's a mistake there. This is 25 point. There's a couple mistakes on this. This should be 25.1, and it should be a negative quantity. All right? This should be a negative quantity. So that could be confusing. This is negative 25.71. Is that right? Let me check that. That doesn't look right at all. So we're going to say 31.3 minus 88.4. Oh, it's 57.1. All right, so let me tell you what's going on here. I've seen this multiple times. This 2 is actually a negative. So it's negative 57.1. There's a mistake there. Yeah, it didn't make sense when I said 25. I said, oh, okay. So I can see this is a major problem here. This is not correct. And it should be negative. That's important. And that's what this 2 is. It's actually, I've seen this typo before. This 2, if you look on the keyboard, no, it's not that. I don't know. For some reason, I've seen this mistake before, though. All right. So let's look at maybe the next slide looks better. All right. So here's what we've done. We've got the specific heat of water, the mass of the water, the temperature change of the water, and it is a positive value because the water absorbed the heat. This is how many joules of heat the water absorbed. So whatever the water absorbed, the pellet released. So that's where the trick is right there. Q of the system is negative Q of the surroundings. We saw that. Here is actually where it's applied. So now you know the Q of the pellet. You don't know what the heat capacity of the pellet is, but you know the temperature change of the pellet. And here they have it correct. All right, so this one is correct. And so we find out the heat capacity when we divide this. Yeah, let's check this to make sure that's the right answer. That looks weird too. There's going to be multiple problems here. All right, so let's take negative 3242. Negative 3242.6. Divide that by negative 57.1. And we get 56.7. And it rounds up to 57. So this is correct. That is the correct answer there. All right. That's bad problems when these two things come out to looking the same here. So anyways, but that is the correct answer. 57 joules per degree Celsius. All right. So constant pressure calorimetry. When do you use it? Heat of neutralization. You might have done this in the lab where you poured hydrochloric acid, sodium hydroxide. So this is what you did. You measured the temperature of the hydrochloric acid. You measured the temperature of the sodium hydroxide, and they're around 25 degrees Celsius, and they should be the same temperature if they've been sitting in the lab together. You pour those into a coffee cup, and the acid reacts with the sodium hydroxide. We form water and a salt. And this is an exothermic process. It actually warms up. So we can actually calculate the delta H of neutralization. Delta H of neutralization. And it would be, and we would make that in kilojoules per mole, not joules per mole, just like they have there. Heat of ionization. You could, this one's a little trickier to do in the lab. But you can definitely do these. Heat of fusion, that's when solid ice melts to liquid water. And then you could do heat of vaporization when you go from liquid water to gaseous water. Again, notice these are endothermic processes because you're reducing the intermolecular force between the molecules. And you know that today. You know this more than they know that you know it because we've already had chapter 11 on intermolecular forces at this point. All right? Just like you know, this probably is going to be, what you're doing here is breaking the bond between the hydrogen and the hydroxide and the OH, and you're ionizing it. And so you would expect that to be an endothermic process as well. All right, let's talk about the next type of calorimetry. This is the calorimetry you use again to determine calories in food items like potato chips and peanut butter or nuts. This is what we use to determine how many calories or joules are in a lump of coal. And so if you work with calorimetry in a lab over and over and you want to know the actual internal energy of the substance, this is the type of calorimetry you're going to do. Now, why don't we do this in the lab? Well, you have to purchase this calorimeter and they're not cheap. It's a lot more expensive than a couple of coffee cups. So you have an insulated jacket or container, and then you have a bucket, the calorimetry bucket. You fill that full of water, and you have a thermometer in this bucket of water, and you have a stirrer to make sure that it's constantly circulating around this container, which is called a bomb. And in the bomb, this is a sealed container usually, and there's a cup here, and you put your peanut butter on this wire right here, and then you fill this full of oxygen, and you ignite it. And then the heat of the peanut butter burning transfers into the water. That causes the temperature of the water to go up. You know what the mass of the water is. So there's the Q equals specific heat of water times the mass of the water times the temperature change of the water. So whatever the Q of the water is equal to negative Q of the sample. And so that's how we figure out how much heat's in that amount of peanut butter. And then if we divide the Q of the sample by how many grams of the sample we have, we know the calories per gram. And so we can then work that out into calories per serving. A serving size 50 grams, and this is 100 calories per gram. 100 calories or 100 joules per gram, and you have 50 gram serving size, you know you've eaten 5,000 calories. So that'd be something very caloric. All right, let's look at a problem. So Q of the calorimeter is equal to negative Q of the reaction, which I call Q of the sample. Q of the calorimeter is equal to the heat capacity of the calorimeter times the temperature change of the calorimeter. So sometimes they do this. They don't only look at the water, they look at the entire calorimeter and come up with the heat capacity of the calorimeter. And so the Q of the reaction is negative, the opposite, the Q of the calorimeter. So that makes sense. That comes back to this equation here, and they just substituted that in here, and we get that. All right, no big deal there. All right, so let's look at a problem. So famous Amos, we'd like to know a bite-sized chocolate chip cookie. We'd like to know we got 7.25 grams burned in a bomb calorimeter. We'd like to determine its energy content. So we're trying to figure out how many calories or joules of energy are in a 7.25 gram sample of a famous Amos cookie. So the first thing is the heat capacity of the calorimeter has to be determined. Usually that's done by, we have a standard thing like benzoic acid or something like that. We know exactly how much heat it should put out, and so we know how much heat should put out by it, and we can then work that backwards to how much heat the calorimeter absorbs, and then we can determine the heat capacity of the calorimeter. So this has to be standardized before this is a totally different experiment, but you have to find out what the heat capacity of the calorimeter is. During the combustion, the temperature of the water in the calorimeter rises 30.90 degrees Celsius. So you go, oh yeah, now I know. Q of the calorimeter is going to be equal to the heat capacity of the calorimeter times the temperature change of the calorimeter. So that's not bad. And then what we know here is Q of the calorimeter is equal to negative Q of the cookie. All right, so that's the plan of action. To me, these are not that difficult a problem. They're two steps usually. And it's really dealing with those two equations, Q equals cat and Q equals smat. All right, so Q of the reaction equals, of the cookie as I was calling it, is equal to negative Q of the calorimeter. So the calorimeter, there's its heat capacity, there's its change in temperature. So here we have negative Q of the calorimeter, heat capacity, times the temperature change, and that gives us the total number of kilojoules absorbed by the calorimeter, but we're looking at Q of the reaction, so that means how much heat was given off by the famous Amos cookie. So again, this is, they kind of combined a little bit too much. So what we have here is Q of the reaction equals negative Q of the calorimeter. All right? Here's what we know about the calorimeter. And so once we calculate this and we make it negative, that's how much heat would be given off by the cookie. Now, that's not usually good enough for us. We want to know how much heat's given off per gram of cookie. So we have to divide the amount of heat released by the cookie divided by the mass of the cookie to find out what the total number of how much energy in kilojoules is given off by gram. Now that may look strange to you. Normally in America we do calories per gram or kilocalories per gram, but most places in the world use joules to talk about energy in their food. So you've probably seen it on some things. I've seen it on little sports packets or something that's in kilojoules. And just remember, when we're talking about food items, we're in the realm of kilojoules and kilocalories, not calories and joules. We're talking about, remember, a calorie is just the amount of heat to raise 1 gram of water 1 degree Celsius. So when we're calculating food items, it better be in kilocalories or kilojoules in size. All right, that's where we're going to stop today. I've got one more lecture for Chapter 5, and hopefully I'll produce that either this afternoon or tomorrow. But we got one more lecture on Chapter 5. Again, if you're having difficulties, you're not understanding this, read the book first, watch the videos, and email me. That's the way we're going to communicate this week. So email me, let me know what questions you have, and I'll be glad to answer those within 24 hours. All right, thank you.